Hello students, welcome to KJ Akshar Academy YouTube channel. In this session, I am going to discuss heat transfer. Problems on thermal conduction part 1. If you like this video, please subscribe to our channel. Please share your valuable comments in the comment section. Okay, let us go to the today's session. First one. One face of a copper plate of area 5 cm square and thickness 0.01 meters is in contact with boiling water at 100 degrees centigrade. The other face is at 0 degrees centigrade. In steady state, find the heat conducted in 1 second. The given as thermal conductivity K is equals to 400 watt per meter Kelvin. Now let us go to the solution. Here we have to calculate heat conducted in 1 second. Given in this question area as 5 centimeter square, converting into meters, 5 into 10 to the power of minus 4 meter square, and thickness they given as L 0.01 centimeter, and theta 1 and theta 2 they given as theta 1 as 100 degree centigrade and theta 2 as 0 degree centigrade, and K they given as thermal conductivity they given as 400 watt meter inverse Kelvin inverse. Now we have to calculate rate of flow of heat. Rate of flow of heat. H is equals to Q by T we have to calculate. Now Q is equals to Ka theta 1 minus theta 2 into T by L. So now H is equals to Q by T. So substituting values in this, K nothing but 400 and area they given as 5 centimeter square, converting into meter square, 5 into 10 to the power of minus 4 of theta 1 minus theta 2, 100 minus 0 by L. L they given as 0.01. Q is equals to Ka of theta 1 minus theta 2 into T by L. So H is equals to Q by T. T gets cancels. Now that is equals to 10 to the power of minus 4. 400 into 5, nothing but 2000 into 10 to the power of minus 4 into 100 by 0.01 can be written as 1 by 100. So 10 to the power of minus 4 nothing but these zeros, these two zeros, and 10 to the power of minus 4 gets cancels. So that is equals to 20 into this 100 reciprocal into 100. So 20 into 100 2000. So H is equals to, we are getting 2000. This can be written as 2 into 10 cube joule per second. So heat conducted in 1 second, that is equals to 2 into 10 to the power of or 10 cube, 2 into 10 cube joules per second. Okay, next we will go to the next question. A 3 centimeter cube of iron has one face at 100 degree centigrade and other in block of ice at 0 degree centigrade. If conductivity of iron is 0.2 CGS units and L for latent heat for ice is 80 calorie per gram, then the amount of ice that melts in 10 minutes is. Here in this question they give an assumed steady state heat transfer. So now let us go to the solution. Here we have to calculate the amount of ice that melts in 10 minutes. Okay, now in this question they given as length of cube or one side, that is 3 centimeter, and area nothing but side square, that is L square. So that is 3 square 9 centimeter square, and theta 1 and theta 2 they given as theta 1 100 degree centigrade and theta 2 0 degree centigrade, and K they given as conductivity of iron they given as 0.2 CGS units, and latent heat of ice they given as 80 calorie per gram. T is equals to they given 10 minutes, converting into seconds 10 into 60, so that is equals to 600 seconds. Now we have to calculate amount of melting ice, amount of melting ice, amount of melting of ice, that is M we have to calculate. So Q is equals to K A of theta 1 minus theta 2 into T by L. Q is equals to ml. So that is equals to Ka of theta 1 minus theta 2 into T by L. M is equals to Ka of theta 1 minus theta 2 into T by L into L. Now substituting all values in this, we get K 0.2 and A 9 they given us, and theta 1 minus theta 2 100 minus 0 100, and T 600 seconds converting into 10 minutes, and L 3 into here latent heat of ice they given as 80. Now here 0 gets cancels, 3 ones 3 threes, and here 2 0.1s are 2 fours are 4 ones are 4 4 twos are 8 4 fives are 20, and here 25 threes are 75, here 0.1 nothing but 1 by 10, 75 into 60, 0 gets cancels, 75 into 6, 6 5s are 30, 6 7 are 42, 450 grams. So M is equals to, we are getting M is equals to 450 grams. Okay. In this question, two vessels made of different materials are identical in all aspects. The same quantity of ice filled in them gets melted in 27 minutes and 45 minutes. when they placed in same surroundings. If thermal conductivity of material of first vessel is 180 watt meter per Kelvin, then thermal conductivity of material of second vessel will be. Here we have to calculate the thermal conductivity of second vessel. Now let us go to the solution. Given time T1 is equals to 1 is in 27 minutes and another one is T2 that is equals to 45 minutes, and they given as thermal conductivity K as 180 watt meter inverse Kelvin inverse, and we have to calculate the thermal conductivity of second vessel. Here M1 is equals to M2. Both masses are equal. So that is K1A delta theta T1 by L into L. So that is equals to K2A delta theta T2 by L into L. Here A delta theta, here also A delta theta gets cancels and L gets cancels. K1 T1 is equals to K2 T2. K1 T1 is equals to K2 T2. So from this K2 is equals to K1 T1 by T2. Substituting K1 nothing but 180 into 27 by 45. 45 ones are 45 fours are 27 into 4. So K2 is equals to 108 watt meter inverse Kelvin inverse. This is the thermal conductivity of the second case. Okay. So K2 is equals to, we are getting 108 watt meter inverse Kelvin inverse. Okay. Next we will go to the next question. The ratio of radii of two cylindrical rods of same material 2:1 and ratio of their lengths is 2:3. Their ends are maintained at same temperature difference. If rate of flow of heat in the longer rod is 2 calorie per second, then in the shorter rod will be, here we have to calculate rate of flow of heat in the shorter rod we have to calculate. Let us go to the solution. K1 is equals to K2. R1 by R2 they given as 2:1 and L1 by L2 they given as ratio of lengths, that is 2:3, and they are maintaining the same temperature difference. Delta theta 1 is equals to delta theta 2. So H2 is equals to, they given as 2 calorie per second. Then we have to calculate H1. Rate of flow of heat in the shorter rod we have to calculate. H is equals to rate of flow of heat, H is equals to Ka delta theta by L. Next, H is proportional to A by L, that is directly proportional to R square by L. Since A is equals to area is equals to pi R square. So from this H1 by H2 is equals to R1 by R2 whole square into L2 by L1. Substituting values, H1 by 2 into 2 by 1 whole square into 3 by 2. So that is equals to 2 to the 4, 4 by 1 into 3 by 2, 2 ones, 2 twos. So H1 is equals to, we are getting, this is H1 by 2. So H1 is equal to, taking cross multiplication, here 2 3s are 6, 6 into 2, 6. So now H1 is equals to 2 into 6, that is equals to 12 calorie per second. So rate of flow of heat in the shorter end H1 is equals to, we are getting 12 calorie per second. Okay, next we will go to the next question. A rod of length 1 meter having cross-sectional area 0.75 meter square conducts heat at 6000 joules per second. Then the temperature difference across the rod is, if K is equals to, they given as 200 watt per meter Kelvin. Now let us go to the solution. Here we have to calculate temperature difference. Here they given as length 1 meter and area of cross section 0.75. So this can be written as 3 by 4 meter square, and rate of flow of heat is equal to Q by T, that is equals to, they given as 6000 joules per second, and conductivity K is equals to, they given as 200, and we have to calculate temperature difference delta theta. H is equals to Ka delta theta by L. So from this, delta theta is equals to, can be written as HL by Ka. So now substituting values in this, we get delta theta is equals to H 6000 into 1 by K they given as 200 into A area they given as 3 by 4. Now 4 ones, 4 fives, 20, 50. So this implies 6000 by 50 into 3, 150. 0 0 gets cancels. Here 15 ones are 15 fours are 0. So delta theta is equals to, we are getting 40 degree centigrade. So temperature difference delta theta is equals to, we are getting 40 degree centigrade. So therefore delta theta is equals to 40 degree centigrade. Okay, next we will go to the next question. In the steady state, the two ends of a meter rod are 30 degree centigrade and 20 degree centigrade. The temperature or the 40th centimeter from the end at higher temperature is. Here we have to calculate the temperature at higher end. Now let us go to the solution. This is the rod. Temperatures are 30 degree centigrade and 20 degree centigrade. The length of the rod is 100 centimeter. Now L1 is equals to 40th centimeter from the end at the higher temperature we have to calculate. So L1 is equals to 40 centimeter and L2 is equals to 60 centimeter. Here this is H1 and it is H2. Theta is equals to, we have to calculate. So K1 is equals to K2 and its areas also equal. A1 is equals to A2, L1 is equal to 40 centimeter and L2 is equals to 60 centimeter. Junction temperature junction temperature theta we have to calculate. In steady state, H1 is equals to H2. Rate of flow of heat 2 are same. So next, K A theta 1 minus theta by L1 is equals to K A theta minus theta 2 by L2. K A gets cancels. Substituting values, 30 minus theta by L1 nothing but 40, that is equals to, now theta we have to calculate, and theta to 20 by L to 60. Here 22 za 23 za. So taking cross multiplication, 3 into 30 minus theta, that is equals to 2 into theta minus 20. 33 is 90 minus 3 theta is equals to 2 theta minus 220 is 40. So minus 3 theta going this side plus. So 90 plus 40 is equals to 3 theta plus 2 theta. So this can be written as 5 theta is equals to 130. So theta is equals to 130 by 5. 5 2's 10, 5 6 are 30. So 26 degrees centigrade. So junction temperature, that is theta is equals to 26 degrees centigrade. Okay. Next we will go to the next question. A slab consists of two parallel layers of copper and brass of the same thickness and having thermal conductivities in the ratio 1:4. If the free face of brass is at 100 degrees centigrade and that of copper at 0 degrees centigrade, the temperature of interface is, we have to calculate the temperature of interface. Now let us go to the solution. L1 is equals to L2, K1 by K2 is equals to 1 by 4, theta 2 is equals to, they given as 100 degrees centigrade, and theta 1 they given as 0 degrees centigrade. A1 is equals to A2. Junction temperature we have to calculate. So junction temperature theta is equals to question mark. In steady state, H1 is equals to H2. In steady state, H1 is equals to H2. Now substituting formulas, H1 nothing but K1 A1 theta minus theta 1 by L1, that is equals to K2 A2 theta 2 minus theta by L2. Here A1 is equals to A2, L1 is equals to L2. So A1 A2 L1 L2 gets cancels, and the remaining is theta minus 0. Theta minus 0 is equals to K1 and here K2 nothing but K1 by K2 they given as 1:4. So K nothing but 4 K1 of 100 minus theta. Now K1 gets cancels. Theta minus 0 theta. Theta is equals to 400 minus 4 into theta. So 4 theta coming this side, that is plus 4 theta is equals to 400. 4 theta plus theta, 5 theta is equals to 400. Theta is equals to 400 by 5. 5 ones, 5 eights, 0. So that is equals to 80 degree centigrade. So the junction temperature theta is equals to 80 degree centigrade. Okay. Next we will go to the next question. Three metal rods of coefficient of thermal conductivities K1, K, 2K, 3K conducts heats of 3Q, 2Q, Q per second through unit area. Then the ratio of temperature gradients are. Now let us go to the solution. K1 is to K2 is to K3 is equals to, they given as K, 2K and 3K. So that is equals to 1 is to 2 is to 3. And similarly H1 is to H2 is to H3, that is equals to 3Q, 2Q and Q. This 3 is to 2 is to 1. So H is equals to Ka delta theta by L. So from this H is directly proportional to K delta theta. So from this it can be written as delta theta is directly proportional to H by K. So the ratio of temperature differences are delta theta 1 is to delta theta 2 is to delta theta 3, that is equals to H1 by K1, H2 by K2 is to H3 by K3. Now substituting 3 by 1 is to 2 by 2 is to 1 by 3. So these two gets cancels. 3 is to 1 is to 1 by 3. So taking reciprocal, 3 3s are 9, 3 and 3 by 3. So overall 9 is to 3 is to 1. So the ratio of temperature differences are delta theta 1 is to delta theta 2 is to delta theta 3 is equals to 9 is to 3 is to 1. Okay, next we will go to the next question. Two slabs A and B of equal surface area are placed one over the other such that their surfaces are completely in contact. The thickness and coefficient of thermal conductivities of slab A is twice that of B. The first surface of A is maintained at 100 degrees centigrade while the second surface of slab B is maintained at 25 degrees centigrade. The temperature at the contact of their surfaces is. Here we have to calculate temperature maintained at the contact of their surface. Now let us go to the solution. Length of a slab, that is equals to twice that of, they given us here the thickness and the coefficient of thermal conductivity of slab A is twice that of B. So that's why LA is equals to 2 into LB. Similarly, KA is equals to 2 into KB. Theta 1 they given as 100 degrees centigrade and theta 2 they given as 25 degrees centigrade. We have to calculate junction temperature theta is equals to question mark. Okay. Next, this is A, two rods A and B and their thermal conductivities K1 and K2, temperatures theta 1, theta 2, their lengths L1 and L2, junction temperature is theta, and rate of flow of heats are H1 and H2. Now in steady state, H1 is equals to H2. So H1 nothing but K A into theta 1 minus theta by LA, length of the rod A. So that is equals to KB A of theta minus theta 2 by LB. Here A gets cancels. They given as twice that of this A rod. So 2 into KB 100 minus theta by 2 into LB, that is equals to KB of theta minus 25 by LB gets cancels, KB also gets cancels. So here 2 into this 2 gets cancels. 100 minus theta is equals to theta minus 25. So 100 coming this side plus here 100 minus 25 plus 25, theta minus theta plus theta. So 2 theta is equals to 125. Theta is equals to 125 by 2. 125 by 2. 2 ones 262.5. So that implies junction temperature theta is equals to, we are getting 62.5 degree centigrade. 62.5. Okay, next we will go to the next question. Next one, two cylindrical rods of the same material have the same temperature difference between their ends. The ratio of the rates of flow of heat through them is 1:8. The radii of the rods are in the ratio 1:2. What is the ratio of their lengths? Here we have to calculate the ratio of their lengths. Let us go to the solution. In this question they given as they are having their thermal conductivities are same and the temperature difference also same, that is delta theta 1 is equals to delta theta 2, and they given as rate of flow of heat H1 by H2, that is equals to 1 by 8, and R1 by R2, the ratio of radii of rods they given as 1:2. So we have to calculate ratio of their lengths L1 by L2. So H is equals to rate of flow of heat, H is equals to Ka delta theta by L. From this L is equals to Ka delta theta by H. Here now next L is equals to K A nothing but area pi r square delta theta by H. So L is proportional to r square by H. So from this L1 by L2 is equals to R1 by R2 whole square into H2 by H1. Now substituting R1 by R2 1 by 2 whole square, H2 by H1 8 by 1. 1 by 2 whole square 1 by 4 into 8 by 1. 4 ones 4 twos, so 2 by 1. So the ratio of their lengths L1 by L2 is equals to 2 by 1. So finally therefore ratio of their lengths L1 by L2 is equals to 2 by 1. Okay. Thanks for watching this video.